السلام عليكم ورحمة الله وبركاته. بسم الله الرحمن الرحيم. Inshallah, today we'll start a very important session in the course. Of course, all sessions are important, but this is very important, which is about neural networks. Neural networks is a very hot topic now, not only in machine learning, but in computer science in general. Okay, so this is very important topic to really pay attention for. طيب. The foundation of so this is the content that we will cover inshallah in the first week. Inshallah, we will cover neural networks at least in 2 weeks, and we might take actually part of the last week also. So this week we will focus on 4 things. What are neural networks? What is how they look like? How to make prediction given an input example? Why or whether they are actually really powerful? And the last one is what is backpropagation, which is the technique that we use for training. Today, inshallah, we'll at least cover the first 2. I hope also part of the third, and then backpropagation will be covered starting next lecture. The foundation of neural networks is perceptron, which you saw before. The inspiration is, of course, biological. If you remember, we discussed that before. We saw that before. Each neuron has incoming connections from the other neurons. Okay, there are signals coming to the neuron, and then based on the strength of these signals and incoming signals, and the strength of the connections themselves, the neuron can fire or not. Fire means it will have an output signal which will be sent to the other connected neurons. So this is the idea of a neuron, and it was modeled by the perceptron. So the connections were modeled by the weights. So this is like the neuron. The neuron has incoming signals from the other neurons through the connections. So the strength of the connections were modeled by the weights. We have a weighted sum, and then the weighted sum goes through a step function or a sign function. Okay, and if you remember that the decision boundary of perceptron is very simple, which is just a line. Okay, but it was a good classifier. Okay, although it's very simple, but it is for some applications it is really effective. So the idea is to make use of the idea of perceptron, but to stack layers of them together. So each node here is considered a perceptron. Okay, and a list of neurons, or we call them also units, is called a layer. Okay, so this is one layer, this is another layer of neurons, that's another layer of neurons, and so on. Okay, in a neural network we have one input layer always, we also have one output layer always, and we have 0 or more layers in between. We call them hidden layers, because they are not input, they are not output, they are called hidden layers. Okay, each layer, as I said, is a set of neurons. Each neuron is connected, as you see, is connected by connections from the neurons from the previous layer. Okay, and the output of a neuron is going through connections to all the neurons of the next layer. Okay, you see the architecture here. So the connections don't go through neurons of the same layer, and they don't jump from one neuron in a layer to one neuron in far away layer. No, the connections are always between consecutive layers. Okay, for each neuron, the input to it comes through connections from all the neurons in the previous layer, and the output from that node, or from that neuron, or from that unit, is copied through all the connections from it to all the neurons in the next layer. Of course, each connection here as in the perceptron. So this is like layers or stack of perceptrons. Each perceptron has incoming connections. Each connection has a weight, right? Like in perceptron, we have weights, right? So here, each connection between two neurons has a weight, and of course, each neuron also has a bias, as we had in perceptron. So this is called multi-layer perceptron, or MLP. Neural networks in general is called multi-layer perceptron. So this kind of neural networks in particular, which is the regular neural networks. We call them also feed-forward neural networks. We'll know the reason soon, inshallah, today. And it is also called multi-layer perceptron. Okay? Any question about this? Right. Why would we want to do that? We had perceptron. Okay, now we have many of them and connected in a kind of strange way. Okay, why do we need to connect many of them if one is good enough? Yes. Okay. Now we can have multiple. Now we can have a way to classify between multiple classes. Will increase. Okay, it might increase the accuracy for maybe a simpler reason. If you remember perceptron, it was a linear model, right? But life is not linear. Linear is very simple. Okay, so we would like to have a classifier that is non-linear to maybe help more in complex classification problems. In complex classification problems, we might need non-linear decision boundaries. Okay, perceptron has a linear decision boundary. Okay, but in some cases, or many cases actually, in real life, we have non-linear. We need non-linear decision boundaries. We need to model much more complex functions than linear. So having multi-layer or connecting multiple perceptrons this way will allow us to discover more complex decision boundaries than just linear boundaries. Okay, and of course, as you said, now we have a way to also have multi-class classification, but we had also that before, right? So that's not very specific to neural networks. We have others. Type. Is that the first one to be actually nonlinear? Did we study nonlinear classifiers before? Or all the classifiers that we study were linear? Decision trees, of course, are nonlinear. The boundaries are really complex. What else? KNN also were not linear. What else? How about perceptron? Okay. How about logistic regression? Is it linear or not? Is it linear? Just a couple of days, actually 3 days ago, we studied it, right? It was linear? The sigmoid function is linear? Of course not. Okay, so logistic regression is non-linear. Okay, but the idea here is that the neural network, as we will see, is much more powerful. Okay, much more powerful. It's much more complex and thus much more powerful. So it can really learn much more complex functions. Right. Now let's see how neural networks actually work. The first example of a neural network is a network that has just one input layer. Of course, always we have one input layer, and we always have one output layer. But the idea here is that we don't have any hidden layer. Okay, did you see that before? Actually, this is perceptron only. Okay, type. In perceptron, we didn't talk about layers, right? Actually, this is just here in neural network is just a terminology. The input layer here is not a layer of. The input layer here is not a layer of neurons, actually. It's just the input vector. So every circle here is not a neuron, is not a perceptron. It's just a number, it's a feature value. Okay, so the input vector, each feature has a value that will be just the one circle in one circle in the input layer. Okay, and of course this is the here the output layer is just one neuron, so this is exactly perceptron. So we have input here x1, x2, x3. Let me write it inside so that you can really maybe get it better. So this is x1, x2, x3, x4. So we have 4 features, okay? And this is W1 here, W2 here, W3 here, W4 here. And there's a bias here. So the weighted sum is sigma Wi xi plus b. And that would be an input to in perceptron, the input to the sine function or the step function. Okay, so this is called one layer neural network, although it's just one perceptron, but the input is considered it looks like a layer here in the architecture, but it is called one layer because we have one layer of weights. So the number of layers in a neural network is the number of layers of weights. Here we have one layer of weights. Okay, so this is one layer neural network. Okay, any question about this? Right. Can we have one layer neural network with 2 output nodes? Of course, we can add another neuron here. Okay, and it has to be connected to all the neurons from the previous layer. So there must be connection here, connection here, connection here, connection here. Will they have different weights than the weights that we already yes, of course. Each connection has a different weight, has its own weight. Okay, so it won't be 1, 2, 3, 4, maybe W5, W6, W7, W8. Okay, but they are also multiplied with the same input vector or from the input layer. Okay, type. In this case, is it one layer neural network or now there are 2? It is still one. It is still one. Okay, this is still one layer, but one layer neural network, but the output layer has 2 neurons. Okay, is that clear? No, the input layer must be always 1 because we have one vector of input. Okay. Type. How many nodes how many units in the input layer do we have? Number of features. Depending on the number of features. Okay. Type. How many output neurons in the output layer? Here we have 2. But can we have more? What's the idea of having more? Multiple classes. Each node actually represents one class. Because the output, as you will see, for the output layer, each neuron will have a score at the end. That will be the score for that specific class. Yes. Say it again. Because these are different connections. Each connection has its own weight. Yes. Type. Just a second. Okay. Let me call these, but it will be really hard. But let's say that this is W5, this is W6, this is W7, and this is W8. Okay. What will be the value, the output value for that node? Let's say that this is B1. And this is B2. What will be the output, the value for this node? The weighted sum. Okay, it will be x1 W5 plus x2 W6 plus x3 W7 plus x4 W8 plus B2, all of that. Okay, is that clear now? Any other questions? Type. This one is 2-layer neural network. Now it is multi-layer perceptron. So here we have 2 layers. Why do we have 2 layers? Because we have 2 layers of weights. This is a layer of weights, and that's another layer of weights. Okay, and as you see, each neuron has connections, has incoming connections from all neurons in the previous layer. So for example, this one, so this one has connection from this node, from that node, from that node, from that node. Okay, so each one has connections from all the previous nodes. Okay, and the output go to all the nodes in the next layer. Of course, here in the output layer we have just one, so we have one connection from each node in the hidden layer. How many hidden layers we have here? One, which is this layer. This is the input layer, and that's the output layer. One hidden layer, and this network is called 2-layer because we have 2 layers of weights. Type. If I ask you how many weights we have here in this network, yes, in the whole network. 4 times 3. You mean here, right? So here 4 times 3. Okay, that's it. We have 3. We have here also. Okay, so this is 3 times 1. So that's the number of weights. How about the number of biases? Okay, I heard 2. I heard 4. 7. 4 or 7 or 2? 5. 4. Okay. 4 or 7. Type. It's clear, I think. I don't know why it's okay. Nobody said 8. I'm surprised. يعني 7 but not 8. It's yes, very good. So this is not neurons. The input layer is not neurons. Okay, these are not perceptrons. Okay, the actual neurons are the neurons in the hidden layers and the neurons in the output layer, which are 4, of course. Okay, but I'm surprised someone said 7. Why is it 7? It should be 8, right? You went 8, I think. Okay, that's why. Type. You understand now? It's 4. Each neuron has a bias, so we have 4 biases. Type. How many parameters we have in this network? The weights and the biases are the parameters. Okay. So this is the model that is trained. This is the neural network model that we train. Okay, the weights and the biases. As we did in perceptron, the parameters are the weights and the bias. Here, all the weights and the biases are the parameters of the entire network. Yes. Okay. We'll talk about the computation very soon, but the computation goes in the forward path. Yani goes from one layer to the next, and then to the next one, then to the next one, until we reach the output. Did that answer your question? Any others? Okay. If we zoom into one of them, we have something like this, which we already discussed, right? We have neurons from the previous layer. We have input values, which are x1, x2, x3 from the previous layers, and the weights. So we have the sum, we add the bias, then we apply a function called activation function. So in perceptron, the activation function was always the sign function, okay, or the step function. Here, it's called an activation function or a link function, okay, and it can be something else other than the step function or the sign function. Okay? It can be sigmoid, it can be tanh. We'll talk about that, inshallah, in detail. But generally, it is an activation function. So this weighted sum is, as you see here, is an input to the function f, the activation function. And that will be the output value of that neuron. Okay, is that clear? Type, is that applied only to the output layer or the hidden layer? Where is that applied? Not only the output layer, every neuron, every perceptron, we have this process. Okay, so we have to know the values from the previous neurons so that we can compute the weighted sum. Then we compute the actual output value from the activation function. Then we compute the next layer and then the following layer and so on. Okay. Yes, let's have an example. Okay, let's say that these are the values. These are the values of the input. And let's say that we trained already a model. Okay, trained the model means what? We have the values of the weights and the biases. Okay, so let's say that the value of that weight is 0.3. This one, I'm looking at this node, so I'm only interested in the connections going to this node. So 0.3, 0.2, 0.5, and 0.3. Okay. Now, what will be the value of this neuron? I think that was your question, right? Kind of. Yes, it will be the weighted sum. So the value of this, I will just write it here, 0.1 times 0.3, right? Plus 0.3 times 0.2 plus 0.2 times 0.5 plus 0.7 times 0.3. All of the, and plus the bias. Let's say that the bias here is 0.45. So that would be plus 0.45. That will give us a number, right? Let's say that this number is A. Is that the output value of that neuron? No. The output value of that neuron is f of A. F is the activation function. So we will apply the activation function on A. Okay? Then this will be the output value. Now this output value will be the value of that neuron. Let's say that the output value here is 0.6. And the output value here is 0.4. And the output value here is 0.21. And let's say that the weights here are 0.4, 0.2, 0. Then now we can get the, and the bias here is 0.7. Okay, now we can compute the output value, the output value of this neuron. Same way. Okay, did I answer the question now? The only difference is that usually, first, do you have any question about how to do these calculations? Is it clear? This is called, by the way, forward propagation. You see the propagation of the values goes from one layer to the next layer. Okay, to the next layer, to the next layer until we reach the output layer. The only difference in the output layer is that usually we don't have an activation function for the neurons in the output layer. So just the scores, just the weighted sum and the bias. We don't apply usually an activation function. We don't need it in some cases. Okay. But usually all the neurons in the hidden layers have activation function. Okay. Why? Why we don't have activation function here? Of course we can. Okay, but it depends on the type of classification that you want. Okay, or maybe regression, because you can do regression here. So in regression, you just want to learn real values. So this will be just the weighted sum that you have. Okay. In some cases, we want the values to be always between 0 and 1, so we have to apply a function that will make the values between 0 and 1. So it depends. Okay. Yes?
Can we have different activation functions for different layers?
Okay, I was expecting that question. So the question is, can we have different activation functions in different neurons or in different layers in general? Can we have that? The model doesn't say that you have to have the same activation function. But the norm or the usual way is to have the same one, except the output layer. Okay? But in general, yes, you can use, that will make things much more complex. But in general, you can use different activation functions in different neurons. Yes. But that's not the usual way. Yes. Not the last layer. The function that is applied at each neuron after computing the weighted sum. So we compute. Okay. So here's the process. We have here inputs, right? We have x's, which is the output from the previous node, previous layer, and we have weights. Okay. We compute the sum of the weights and the input values plus the bias. Okay. Then we apply the function f. This is the output value now. At each node, at each neuron. Well, that's what I'm saying. Sorry. It's at every neuron. Every neuron in the hidden layers and the output layer. Of course, every node has its own, as you see here, every node has its own value. I don't see your point. What's your question? Okay, you see this here, Samha? Do you see this? This. This is applied, this is like zooming in every neuron. Okay, every neuron we compute the weighted sum and then apply the activation function. Every neuron everywhere, except of course the input layer, because the input layer are not neurons. These values are the output values for the neuron. I just wrote it inside, but it is actually the output value. Exactly. Yes. The value coming out from the activation function. Okay. What is the input to the activation function? The weighted sum. How do we get the weights? Training. We didn't talk about training yet. Okay. Usually, whenever we study a classifier, we talk about how it works, how we can do the prediction, and then we talk about how we train it. Okay. So here we are talking about how to do the prediction actually. Given that we have an input example, how we can predict the value for that input, given that we already trained the network. Train the network means we know the weights and the biases values. Right. Okay, any question about this? Because these computations are very important to understand. This is how the network will work. Yes. This one specifically is binary classifier. What do you think? Yes, if we don't apply any activation function, this is a regression actually, because it can learn any real value. Okay. If you apply sigmoid, then this will be probability. Then this can be seen as a binary classifier. Okay. Yes. But if we have like 5 classes, usually we have 5 nodes in the output layer. Any other questions? Type. The architecture that we saw is called fully connected. Okay, fully connected, because all the nodes or all the neurons in one layer are fully connected to the neurons in the following layer. Okay, that's not always the case in neural networks, and this is a specific type. of neural network, which is the regular neural networks, okay, that is fully connected. And as you see also in regular neural networks, there is no connection within the same layer. Yani, there's no connection from this node to that node. The connections are always across layers, not within the layers. Okay. Okay, so this is what we said. And also we said that this is the output layer neurons most commonly don't have an activation function. Now, when we say this, when we talk about the size of the network, we mean two things. We mean either the number of neurons or the number of parameters. Okay, and of course they are. We know now how to compute this, right? So, for example, this one, how many neurons we have? For this one, I mean this network. First, how many layers we have? Is that 2 layer or 3 layer or 1 layer or 4 layer? 3 layers. Why is that? Okay, you can think of it that way. You don't count the input layer, or you can, I think, better to think about it as layers of weights. Okay, so we have 3 layers of weights here. 1, 2, 3. Okay, type. How many neurons we have? 9. Okay, because these are not neurons. There's no computation here. The neurons are where the computations happen. Okay, so there's no computations here. These are the neurons, and of course we also can compute the parameters, right? Which are the weights and the biases. About the activation functions, as I said, they are also called link functions, and they are non-linear. Okay, they are non-linear, and this is very important, right? Because as we said, we want to learn complex functions. Okay, and complex functions are non-linear. Linear are just the simplest one. There are many used activation functions. We saw, of course, the sign or the step. We also saw the sigmoid function, right? Where did we saw the sigmoid function? Okay, in the previous lecture, in the heuristic regression. There is also one that is commonly used, which is the hyperbolic tangent, tanh. We'll talk about it, and also really one. There are many other functions that, inshallah, we'll talk about them later. And the most important thing about them is that they are all non-linear. Step function is this very special case. We usually don't use it actually in neural networks at all. But that was used in perceptron. Now your question: what happens if the hidden units are the identity function? What do you mean by identity function? Identity function means the output will be equal to the input, which means they are not there. You can think of it that way. So as you said, what if we remove the activation functions completely? What will happen? And imagine in the network that we have before, we just remove the function f completely. What will happen? Let's look at this. What if we remove the function? Then what will be the output value of this node? Just the weighted sum, right? So it will be just weighted sum. Sorry. Will be the weighted sum, right? How about this one? Also will be weighted sum. Also will be weighted sum. Also will be weighted sum. Type. How about this one? It will be weighted sum also. Okay, weighted sum of the input. Okay, sum of the input, weighted sum of the input. I mean the input which is the output of the hidden layer. Type. Then what will be the output value for this? It's just a weighted sum of what? This one is a weighted sum of these, right? Of each of these, right? Which is itself a weighted sum of of the input. Okay, so eventually the output value from each neuron in the output layer will be a weighted sum of the input, which is linear, right? Which is linear. So if we removed, because it's a linear combination of the input, right? So if we remove the activation functions completely from all the network, then this will be reduced to what? To linear, which is just one perceptron, right? Which is one perceptron. So we actually destroy the entire network. It's meaningless. It's just one perceptron at the end. Although it's done on layers, but it is just a linear model. Okay. So of course, the non-linearity is not the non-linear. The activation functions are important. Yes. Yes, eventually, if you expand it back, you will find it will be a weighted sum of the input, a linear sum of the input. Okay? So it can be replaced by just one perceptron. Any other questions about that? Is that clear? Right. Now, I think we have done this already, the prediction, how the prediction is done. Here we assume that we already learned the model, we already learned the weights and the bias. We want to do the prediction. Prediction is done by what we call forward propagation, as we did it. From the input, we get the values for the first hidden layer, then the second hidden layer, then the third, then the fourth, then the output layer. Okay. In this specific case, we have one hidden layer only. So in this algorithm shows us how to actually compute this. So in this algorithm, the weights of the hidden layer is W, and the weights of the output layer, the parameters of the output layer, is called V. Okay. So if we want to do the prediction, let's say that we have an input vector here, X. Let's say that we have X as an input. So if we call the set of weights incoming to this node W1, and this is a vector now. Okay, so W1 is a vector of all the weights coming to this node. So in order to compute, assuming that there is no biases for now, okay, it's just for simplicity. In order to compute the weighted sum for that node, what should we do? X is a vector, W1 is a vector, we just have the dot product, right? So that will be W1 X, right? And then applying the function to it. This is exactly what we do here. So for each hidden unit, this algorithm is specific to this network, okay, to the two-layer network. Assuming that the weights, the weights are called W for the first layer and V for the second layer. So we compute for each neuron, for each hidden unit. Unit, by the way, is neuron. Okay, hidden unit means neuron, hidden neuron. For each of them, we compute the weighted sum, which is Wi times X. Then apply the activation function. Here we assume that the activation function is 10H, whatever the function is. This will give us, is that a scalar or a vector? Wi is a vector, right? X is a vector. Vector times vector is scalar. Okay, of course the function will give us also a value. So Hi it's a scalar. It's the output value actually of that node. So this is then H1, this is H2. Do you see the color here? Okay, this is H3. Type. After we compute this, what should we do? Now H1, H2, H3 is H vector. We can call it H as a vector. Now if we have a vector H and we have a vector V, which are the weights here, then to compute the value of this node, we just multiply H by V, right? Or V by H. That's this value, which is the predicted value now from that network for that example. Okay, of course, if we have multiple layers, we will do that in multiple steps. So we'll do it for the first hidden layer, then the second. Right. Do we have to wait? Yani, can we do the first and the second in parallel? No, because we have to get the values for the first hidden layer first, and then we get the values of the second layer, then we get the value for the third layer, and so on. But what we can do in parallel is the computation of H1 and H2 and H3, right? Because they are independent. You see, H1 depends on the weights and the weights incoming to it and the input. H2, the weights incoming to it and the input. So these ones can be done in parallel. In reality, actually, we have the weight matrix. So W is a matrix, actually. Each row is the weight vector for one hidden unit. Okay, so instead of doing it as a loop like that, actually this is done by a matrix vector multiplication. We just multiply W as a matrix by X as a vector. And we get the H as a vector. So H will be the multiplication of W as a matrix and X as a vector. The matrix will be, each row will be hidden unit, and each column will be an input unit from the previous layer. Okay, so here it will be 4 by 3 actually. So we have actually 3 by 4, sorry. Okay, is this clear? This matrix vector multiplication? Instead of doing it one by one, we can just do it as a whole by matrix times a vector. That will give us the whole vector, okay, which are the output values for the entire hidden layer. Okay, question? For this, in this algorithm, there is no activation value for the activation function for the output. Yeah. If there is, then you can apply it, of course, on the multiplication. Any other questions? Yes. We what? Yes, you can add it, of course. It will be just added as a vector. If you will do this matrix multiplication, then you add it as a vector. This is just for computations, but theoretically, you can of course do each one separately. I think easier to understand as we did it before, okay? But to make it efficient computations, then we should use matrix and vector operations, okay? طيب, we'll continue inshallah next time. Assalamu alaikum.